All right, so I'll solve these two and then we'll move on to the next set. So I'm going to change this to log base 3 of 4 equals 3 minus 2x. I'll subtract 3 from each side. My goal is to get x by itself. Then I'll divide both sides by a negative 2. So x equals log base 3 of 4 minus 3, all divided by a negative 2. I could type that all into my calculator and get a decimal approximation. Let's try this one. So this one comes in a log form, so I'll switch it to an exponent. The base here is a 10. It's common log, so it's a base 10. So you do need to know that, or at least fill it in if you forget. 10 to the second power, so that will be 10 squared, that's 100, equals the argument 3 minus x. So now that's in exponent form. So that's going to be 100. Let's subtract 3 from both sides. So that'll be 97 equals negative x. So x must be negative 97. That's my next one. So I can always take that, plug it in. 3 minus a negative 97 would be 100. Log base 10 of 100 does equal 2, because 10 squared equals 100. That works out. I can plug that back in using what I know about logs or my calculator as well. All right, let's take a look at the next set. This is where we're going to have some other properties, still solving equations. All right, so in this situation, we've got something called the property of equality. I've also heard it called the one-to-one property of equality for exponential equations. And it basically says if you have a couple of exponent expressions equal to each other and the bases match, well, then we can ignore the bases and just solve an equation based on what the powers are. So, but first the bases have to match. So in this situation, I've got 125 to the x power, oh, sorry about that, equals 5 to the x plus 10. So I'm going to make these bases match. I know I can change 125 to 5 to the third. So I'm going to replace 125 with 5 to the third, and then I'll keep my variable or my exponent as a variable x there. And then I'll just rewrite the right side as is. My goal was to get the bases to match, and now they do match. So I can ignore them and just focus on making sure my exponents match. So this, now let's try to make these the same. Let's see. If I subtract x from each side, then I get 2x equals 10. If I divide by 2, then I get x equals 5. And I can always plug that back in, but I don't have any domain restrictions, so I'm not worried about these not working out. Logarithms do have domain restrictions, but I can plug a 5 in here. 125 to the 5th is going to be the same as 5 to the 15th. Some of these with exponents are going to be so large, they may overflow error. They put an overflow error on your calculator, but we'll see. Here's one. We've already done one like this. Changing form. It's only a single exponent, right? This one had one on each side, so we were trying to get the bases to match. This is just a single exponent. So let's just change the form. Log base 2 of 7 equals x. And then you could always use your change of base formula. Common log of 7 divided by the common log of 2. That's from last class in 6.5. That was our change of base formula. It's also on the back of your purple assignment sheet. You can get your decimal approximation that way. So here, let's see, I can definitely turn 100 into a base 10, and this 1 over 10, I can make that a base 10 by giving it a negative exponent. So a negative exponent creates a reciprocal. It makes you flip the fraction. So I'll start with 100. 100 is 10 squared. So I'll replace that. So I replace 100 with 10 squared, and I keep the x. And then I replace 1/10 with 10 to the negative 1 power, right? Because those are equal. So I'm replacing this with what it's equal to. It's a substitution. And then I will keep this power of x minus 3 with it as well. And so now that the bases match, that was my goal with A, so it's my goal here as well. I can ignore the bases and just solve an equation for the powers, distribute that negative 1, negative x plus 3. Add x to both sides, so I get that. And so divide by 3, and x must be 1. I'm going to skip this one. It's very similar to the ones we did on the first page. Don't worry about it. I'm also going to skip this for now, just because I want to make sure we have enough time to go over the different types of equations and inequality solving. So I might just have to come back to this. All right, let's go ahead and flip to the next slide. Otherwise, I'll talk about it in class. If I don't get to it today, there's probably only one problem in the homework. It might be a better conversation to have in person. Let's go ahead and look at the next example set, example 3. So right away, I noticed these are logarithms. The ones on the right are like our first set on the front page because it's a single logarithm equaling some value. So I can rewrite these 2 to the third power equals 5x minus 17, or down here 3 to the fourth power, right? The base stays the base, so the base of the log becomes the base of the exponent, and then the opposite side becomes the power equals 10x minus 9. So I rewrote those. And now I can go through my solving steps. 2 to the third is 8. 3 to the fourth is 81. Right? So these are just linear equations. I'm going to add 17 and divide by 5. So that becomes 25 equals 5x. Divide by 5, x equals 5. And over here I'm going to add 9. So that becomes 90. Equals 10x, divide by 10, and x equals 9. It is important with logarithms that you check your work. Your argument cannot be 0 or a negative value. So for instance, 2 to some power will never give you a negative number. It'll get really close to 0. So we do have some domain restrictions. The argument cannot be 0 or negative. So I'm going to plug this 5 in right here and just make sure that this stays positive. So 5 times 5 is 25, minus 17 is positive 8. So I think we're in good shape. 2 to the third power does equal positive 8. That works. If it made our argument negative, I would have to throw this out, and we're going to call it an extraneous solution. This one's going to work as well. Over here, this is a new set. The difference here is I have a logarithm equals a logarithm. So there's one on each side. And this is similar to the exponent property. If I have a log on each side and the bases match, then if you look at this example here, then I can ignore the logarithm, these happen to be base 2, and just focus on what they're equal to, right? X equals 7, right? So, but the bases have to match, and there can only be one on each side. So these are both log base e, the natural log, and so I can ignore those and just focus on solving the linear equation of the arguments. Subtract an x from each side, add a 7 to each side, divide by 3, and x would be 4. Again, with the logarithm, I'm going to double check. I put a 4 here and I get a positive 9. I put the 4 here and I get 16 minus 7 is a positive 9. So I'm taking the log of positive numbers, so that's going to be fine. This one's super similar. Why don't you give it a shot, and I'll show this answer in the next video, and then we'll move on to the last bit.